Bueno, vamos a empezar, si les parece. Muchas gracias por venir. Sabemos que es más temprano de lo normal, pero bueno. Hoy tenemos como invitado a Félix. En realidad no es tan invitado porque Félix es investigador superior acá en el IAFE, de CONICET en el IAFE. También es miembro titular de la Academia Nacional de Ciencias Exactas, Físicas y Naturales de acá de Argentina. Obtuvo el doctorado en astronomía en la Universidad de La Plata y el título de profesor en filosofía en la Universidad de Buenos Aires. Fue protagonista principal en los descubrimientos de 3 tipos de objetos en el cosmos: los microcuásares en astrofísica de altas energías, las galaxias infrarrojas ultraluminosas y las galaxias enanas de marea. Actualmente investiga en cosmología. Por su trabajo recibió muchas distinciones en Europa, Estados Unidos, Chile y Argentina, entre ellas el doctorado honoris causa en Barcelona, el premio a la excelencia científica de la Comisión de Energía Atómica de Francia y el CONEX a la trayectoria. Bueno, le damos la bienvenida, muchas gracias.
Gracias. ¿Se me escucha bien?
Gracias.
Yo creo que necesito un micrófono.
No tenemos, pero si mira la cámara, es la que está tomando la cámara.
Sí.
Es la cámara la que toma la voz.
Bueno, gracias por su atención, por haber venido. Bueno, yo lo que quiero señalar es que los agujeros negros, ¿podría hablar en inglés? ¿Hay alguien que no entiende inglés? Que prefiere que hable en español. Yo hablo en español, pero me lleva más tiempo porque tengo que encontrar las palabras.
Adelante. Sí, adelante.
Yeah. Okay, because since many years, my work, when I do astronomy, I think in English. Really. Even during my period in France. In France, nowadays, when I arrived there and here, I think it was in 19, you had to speak in French. But then things started to change. Now it's full of Chinese, come as postdocs, the new kind. Well, the astrophysical black hole is an object in the universe with such a pull that nothing, not even light, can escape from it. And I know that Hawkins, using quantum mechanics, arrives to have things that come out from the black holes, but these are very special, very weak phenomena that this time is completely impossible to observe and to contrast the observation. And in fact, after the Michelson-Morley experiment, Einstein postulated that the speed of light is universal constant. And this is not something immediately intuitive. It goes against intuition. But you remember that the Michelson-Morley experiment, here is Michelson, Einstein, found that an experiment that changed the orientation of physics, because the physicists thought that light was propagating in ether, and if that was the case, depending on the direction of the observations, the speed of light will change. And they had an experiment that showed, against the expectation at that time, at the end of the 19th century, that was not the case. So Einstein proposed, against intuition, that based on that experiment, that the speed of light is a universal constant. And I will show that on the basis of this principle, we are allowed to explain a thing that I have observed, that are the apparent superluminal motions of jets in our galaxy. That was the best observation of the ultra-relativistic jets found until now. And then I will show that the usual and unusual changes in jets of black holes of all mass scales, can be understood in the context of general relativity. The first phenomena were these jets were understood in the context of special relativity, but there are other phenomena that I will show on jets that can be explained on the basis of general relativity. And finally, I will conclude that that black holes, all black holes in the universe, when we grow hidden in the dark, beyond dust. And this is something that we now see in the local universe. I will show the most spectacular case of that. And then in the early universe, observations with the James Webb Telescope show that the new black holes that are rapidly growing are hidden. The X-rays that they should be producing are completely hidden from observation. But we know that they are producing jets because we see these jets either at radio waves or in the infrared. There are other ways to see them. Now, you know, Einstein's theories have many applications, but since I worked on relativistic jets, I thought that the best thing was to speak on something that I have been working for decades. That is relativistic jets, where you cannot understand them unless you use either special relativity or general relativity. And here you can see when I arrived to France, actually I was employed in the year 1990. to work on the scientific exploitation of ultraluminous infrared galaxies, because Europe was ready to launch the first European satellite to observe in the near and far infrared, mid and far infrared whole universe. That was a satellite called infrared space astronomy satellite, and which was a follow-up of the satellite IRAS, infrared astronomical satellite, that was led by NASA. And since I have been working on the most important sources discovered with IRAS, with Dave Sanders, in Europe they needed people that would work on the scientific exploitation of the new European satellite that was the first one for observations in the mid-infrared. But when I arrived, well, I knew that the month before I arrived, Europe had launched in collaboration with Denmark and the Soviet Union at that time, a satellite called Granat, that was the first satellite to prospect the universe in the hard X-rays and soft gamma rays. A big satellite launched from Baikonur, and I was sharing when I arrived in 1990. An office that was transit office, because the new building was going to be finished in a few months, with a theoretical Canadian astronomer, very well known, and he actually discussing with him at that time, 1990, he said that he didn't believe that black holes really existed in our universe, that were imaginative objects. And so people from the satellite came from Granada that were in flight. They came to tell him what were the new things that were coming from this satellite. And, I couldn't stop here, or put something in my ears to block them. And so I started to hear that there were a lot of new sources that should be black holes being discovered in our galaxy, because these were very small sources of hard X-rays and gamma rays. But with this satellite, there was not enough resolution to see where was coming the emission from. So because the resolution in gamma rays is very bad, so degrees, and there are a lot of work. So I said, so my reasoning was, if these objects are sources of gamma rays, they should be sources of relativity that we introduced gradually, and with an instrument like the very large array of radio telescopes, we should spot where this radiation comes. In that case, we could go to the very high resolution points that produce the variable radio emission. We could then identify if they are black holes or not, because black holes could emit dark X-rays and soft gamma rays, stellar mass black holes. And so with the DNA, we determine where were these emission coming from, and so I led observations in the infrared to spot what was going on there, and evidently, well, these were stellar mass black holes, but one would expect from stellar mass black holes that are accreting from companion binary stars. And so we detected first the point source of one of the strongest source, that at that time the physics today portrayed as the potential source of in the galactic center of the annihilation between matter and antimatter that produces a gamma ray emission at 511 kiloelectron volts. And so it was called at that time the great annihilator of antimatter in our galaxy. And so with Luis Felipe Rodriguez, who at that time, yes, he was just coming back to Mexico from several years in Harvard, and he was less. I think he was. I don't know if he was already in his 30s, and he was often the director of the Institute of Astronomy of the UNAM, because there were two big groups fighting between them, and they needed someone from outside to pacify the institute. And this is something that is many times approached, and to have someone also with a different view of what an institute should be, to avoid inbreeding. Yeah? And so he is a very good specialist of observations with the DNA, and so I was surprised after doing many observations is that at the center of the source of the variable source, there were two-sided orientations, jets of radio emission that could reach several parsecs in distance. And so I said, well, this object is similar to what is observed in quasars and extragalactic galaxies, where this phenomenology is believed to produced by supermassive black holes. So I said, well, this is a microquasar, a scale down of a quasar. And so nature put, I didn't put this in the title, I just was a term to, in some way, stimulate the astronomers to think in more general terms. what could happen in quasars could happen in objects in black holes or stellar mass holes. And you can see here that this is a real relativistic motion. This is the point where is the black hole, the stellar black holes, eating a star, and you see that, that the cloud, the plasma cloud that moves to the left, moves faster than the one to the right, and also seems to be brighter than the one moving to the right. And this, I said, well, obviously this might be a relativistic beaming effect, aberration in antisymmetric ejection, and using relativity, the kinetic energy that we estimated. So the conclusion was, looking at this, if this source was at the distance that we believe at that time, that was about 10 kilopascals. And we know that if it is at a distance of 11 kilopascals, is beyond the galactic center and behind our galaxy. This speeds of the actual speeds of the apparent speeds of these jets should be superluminal. And apparent in the article in Nature appear in mayo. 8, as saying it's not the real velocity, it's an apparent velocity due to relativistic aberration. And the kinetic energy of this ejection event that took all this was observed during 1 month, the kinetic energy that we calculated was that it's equivalent to 1/3 of the moon's mass accelerated to a velocity of 98% the speed of light, lo cual is an enormous energy produced during 1 month. And we know that this source is impacting at scales of tens of parsecs the structure of the galaxy, is model. So it took us well, it took us 2 weeks to work out the equations in the context of C as a constant that will account all the phenomenology we were observing. And the idea is that that we could determine also on the basis of special relativity that this source was not beyond our galaxy based on this equation that is derived from all these equations, where you have C as a universal constant over a root square of the product of the proper motions of the two components of the jets. What I wanted to show is that as you will see, as proposed as a postulate, Einstein is a complex. All this jet phenomenology is clearly explained with equations. It took us, I think, more than 2 weeks. And then the following year, in the international Olympics of Physics in Sweden, the first problem for the students that were competing, the best students of the world of physics that were competing, the first problem of 5 problems that they had to solve in something like 1 hour or 1 hour and a half, that was make calculations on this. So I felt ashamed because it took us more than 2 weeks to work out this equation. And they solved it. I mean, the winners, they came as representatives of all countries to this Olympics. They could solve it in 15 minutes. So when I look at how the problem was formulated and in the context, and in fact the problem was used, and there is a problem, and they get the things for them to use these equations. We were already known by the students of physics, because this paper that I showed, I believe it has more than 1,300 references in referee papers. So these students, they knew. The point is that one thing is to solve, to have the capacity to solve a problem. And another thing is to have the intuition to see where is a problem and what steps should be taken to solve it. And this is something that I learned here in Argentina from a professor of astronomy, the way of thinking. That was called JWST in La Plata, a professor of astrophysics, that his attitude as professor was to teach the students to think, and to formulate the most important questions that are finding in research. Well, this is something that in the year 1998, Nature asked us to make progress. It was a paper by invitation because of all the results. And this is a figure of that progress report. in this area, new area of research, where we propose that there is an analogy, a profound analogy between the phenomenology that is produced in supermassive black holes and in mainly in quasars and in microquasars. And usually both objects, black holes, no matter the difference in masses, both classes of black holes that certainly must be of very different origin. I will not go into that because it will be another topic. They response, we propose that they response to the same system of equations with the fact that the scales of distance and time of the phenomenology in the two classes of objects are proportional to the mass of the black hole. So if you want to, if you are interested in physics and you want to see directly the accretion disk, how is it structured? What is its space structure? Space structure. The best thing is to observe supermassive black holes, because in terms of the unit of length, for instance, the Schwarzschild region of the black hole is much. You have much better resolution observing supermassive black holes. This is why the first direct image of an accretion disk around a black hole that was observed with a new array of submillimeter radio telescopes that they don't have still the Nobel Prize. They observed Messier 87, not a microwave, because in terms of the physical terms, the physical unit in supermassive black holes is the Schwarzschild, that is enormous compared with the one in microwaves. Contrary, if you are impatient and you want to see rapidly how the phenomenon takes place, the best thing is to observe microwaves, because the scales of time in microquasars is much shorter than in supermassive black holes. This is why there are, if you are interested in time variability of the phenomena, you observe microquasars. And since the physics equations are the same for both types, you can use them to interpret what might happen in supermassive black. And then when you observe this, you want to see how this are structured in microquasars. Perhaps you have to use analogies that have been observed with the array of video telescopes. And I forgot the name of the array of video telescopes, including Alman, that passed down the first image of the distinction this in material 87, the Sagittarius Space Star. How is called? Event horizon. Yeah. So you use the event horizon. And so I'm working on this, and the other day I asked a colleague that if he could remind me what was observed from the observations with event horizon in M87, because I wanted to use as an analogy to try to understand better of what I was trying to understand in a microquasar, which directly is impossible to observe. Because so there should be a complementary. In this article, we propose that the studies of these two different types of black holes, although they can have very different origins, this should come from stars, and this we still don't know exactly. But you should use both types of observations. Now, besides this sudden event that I showed, there are also in microquasars smooth and continuous changes in the jet axis of black hole low mass X-ray binaries up to 10 of degrees. Low mass X-ray binaries that in low mass sources of X-rays that contain black hole. And here you can see observations that we had in the year 1999. And there is a sort of precession that is a general relativity process that takes place when the black hole spin and the orbital angular momentum of the binary are not aligned. And this general relativity mechanism causes a relativistic force in the disk, namely deform the disk, because the black hole spin impact on the structure of the space time where it is, and changes the orientation of the accretion disk. And you can see here an example. Here in this diagram are shown the observations of two ejection events that took part with 1 month apart in directions of and produce jets with difference in directions of the jets of 10 degrees. And these 2 points here, this is the center of ejection. It's the center of ejection. These two blobs were ejected one before, and they were fading away as they moved away. And these two were ejected more recently, 1 month after the first one. And you can see that the direction of the jets changes. About 10 degrees. And the same can be seen here using BLBA. This is a famous source that is producing the jets at speeds of, we know, of 25% of the speed of light. And you can see that the direction of the jets changes. This is 1 month. And this point is following 1 month. And the jets are oscillating. And this is a phenomenon due to the fact that the black hole, with its spin, interacts with the space-time and produces in the accretion disk this difference in velocities. Here, it is always believed that the jets, the direction of the jets, is perpendicular to the plane of the accretion disk. See, the accretion disk is in this direction. The jets are perpendicular. And if the jets change direction, it's because the disk is doing this. So, and well, this is this is a phenomenon that is commonly observed. Also, supermassive black holes show this type of things. That there are jets that in different centuries have different orientation. So this source that that I showed you is a sort of prototype. And in the year, you can see in the year 1994, when it was realized the orientation of the jets, they remained in that direction for several years. The direction changed slightly, as I showed, in 1999, and then came back to this orientation. And the surprise that was that in the year 2023, the orientation of the jets changed by about, in total, by 30 degrees. And that was too much compared with the usual 10 degrees. So now this is just based on the analysis. We know that this change in direction was produced by a high accretion rate that was produced by the impact of on the disk of the source of stream of very strong stream of high accretion rate of mass. And the point is that after this event, in the year 2024, within 1 year of these observations, the jets came back with the same orientation as they have had in the past. And this is another general relativity phenomena called the Bardeen-Peterson effect, that says that the spin of the black hole is a black hole with a mass of about 11 solar masses, but it's a Kerr black hole that has a very strong spin. It is rotating in itself at 98% of the maximum rotation that can have a black hole. So the strength of this black hole is very strong. And what the Bardeen-Peterson effect says that if the accretion disk went away from the orientation that I tell you the accretion disk should have, it will come back to the precision and orientation that my spin is imposing. And this is what happened. And this is a general relativity effect predicted many years ago. I think it was in the 90s by Bardeen and Peterson. But the point is that in this epoch, we find that our analysis show that the accretion flow that went into the system was within 3 degrees, plus minus 3 degrees of the line of sight. So when the disk was aligned with the line of sight, and this is a very particular orientation that can explain many phenomena, like the X-ray complete obscuration of the source during the epoch of these observations with the James Webb Telescope. I will continue then. So in this case, the orientation was in that direction and then came back. So another phenomenon associated with this, well, this is a historical, my colleague Rodriguez, he did this. He took all the observations during 30 years and put a diagram of the position angle of in the degrees as a function of time. And here you can see the years. In 30 years, and this source has been oscillating, but in 2023, it produced this separation during less than 1 year. So, and one of the questions is, well, that we are discussing, and with this belief, I believe we don't believe each other, the interpretation, but we will see what happened. The other phenomenon that was observed in that epoch, you can see these sources combined with this oscillation. These oscillations can be seen with a fixed, more or less fixed periodicity. And typically, the maximum periodicity that had been observed from this object since its discovery in 1994 was of 24 minutes. So the jets oscillated in space, or the disk oscillated with a period of 24 minutes. But in the epoch when it produced this anomalous change, the period changed to 8 minutes. So it was reduced by a factor of 3, which using the Kepler's law, if during this period in the year 23, the disk had the same circular shape that had in this this would imply that the semi-major axis of the disk has been reduced by 48%, which implies that it has increased the surface density by a factor greater than 4 in the outer parts of the disk. So the disk shrink, and which is consistent with the unprecedented obscuration of the X-rays that are characteristic of black holes, as accreting black holes. The high radio fluxes observed with different telescopes and the high mid-infrared luminosity observed with the WISE and the James Webb Telescope in that epoch. So the question that is open is what may have caused these sudden and transient changes in GRS 1915? It is same. Thank you. Local question. Excuse me, let me take a little water. And, so if something like this happening in the early universe, I mean, you know, the supermassive black holes that we find in the centers of galaxies, they were never like they are today. And they have been growing very early in the universe. With the James Webb, before the James Webb, were known, for instance, 7 supermassive black holes with masses of 10 to the 9 solar masses at redshift of about that corresponded to ages of the universe of about 700 million years. And the question is how they got these very large masses. And this is what is believed that they have been growing from seeds of 10 to the 3 or 10 to the 4 solar masses. And the first results from James Webb were three black holes found at this epoch, and the universe had still about 500 million years in their way to become as massive as 10 to the 9 solar masses. And more recently, the most recent result with the James Webb has been the discovery of abundant objects called little red dots at very compact objects. These are the images in James Webb. They are almost point sources with sizes, with video sizes of in between 35 and 100 parsecs, very bright in colors, probably due to dust, as in the case of JWST 1915, and most of these objects are X-ray obscure, as the black hole in JWST 1915-105. It's very difficult to study these objects that are in general at redshift greater than 4 and observe clearly up to at least redshifts of 10. And these are, you know, these supermassive black holes growing. Some of them stop growing. We don't know why, but the idea is that these objects grow very rapidly. Some of them, not all, very rapidly. So the conclusion is that black holes in the local and early universe grow rapidly in the dark due to super Eddington accretion. In other words, under certain conditions, accretion becomes super Eddington, and black holes grow. And under other conditions that depends on the environment, this accretion, high accretion rate towards the black holes stops. And we don't know sometimes why. I believe this is the conclusion.
La frecuencia tendría que estar muy corrida al rojo, entonces exactamente qué significa que están oscurecidos.
Es que tienen que atravesar los X densidades enormes de columna para llegar a nosotros. Entonces, es inverse Compton. El mecanismo es inverse Compton. Digamos, los X se dispersan muy cerca de la fuente de los X, o sea, de estos agujeros negros. Entonces están oscurecidos y sabemos que siguen activos porque las radioondas sí atraviesan esos medios muy densos y sabemos que los objetos estos son muy activos. Hay, si me permiten, por ejemplo, aquí se ve la evolución en el tiempo de esta fuente. La fuente era antes del año 2019, era muy fuerte en rayos X. Fue así como fue descubierta en 1994. O sea, un cañón en rayos X. Y aquí se ven los rayos X como, en función del tiempo, a partir del año 2018, más o menos, comienza a bajar en el 2020 y todo termina casi en cero, excepto en X, excepto algunas manifestaciones. Pero en radioondas continúa activa. Lo que quiere decir que hay un agujero negro activo produciendo jets en el interior que pueden penetrar todo el medio toda esa columna de densidad en radioondas. Y lo mismo pasa aquí con las radiaciones en el infrarrojo intermedio con el James Webb, con la cámara de imágenes, que se ve que en general estaba muy bajo, pero de repente, cuando nosotros hacemos esas observaciones, no las hacemos nosotros, explotamos esas observaciones del archivo de 2023, se ve cómo en radioondas, en rayos X está muy bajo, excepto algún puntito que subió ahí. En radio produce flares y en el infrarrojo intermedio también produce flares, observado con el James Webb. O sea que ha habido un trabajo de los teóricos de Harvard diciendo que los agujeros negros ahí no están rotando y cosas así. Y yo creo que las cosas son más simples, que simplemente hay densidades de columna enormes y que los agujeros negros que están creciendo y activos en esa época están simplemente oscurecidos dentro de cocoons enormes, muy densos de gas y polvo. En la época temprana del universo, el polvo debería haber sido producido en forma muy temprana, porque los productores rápidos de polvo son las explosiones de supernovas. En los choques se enfría, se produce polvo, al enfriarse el gas que es chocado, y que envuelve estos objetos. Y como se habrían producido una tasa muy alta de estrellas masivas, con masas más altas que 20 masas solares, todas esas estrellas explotan muy rápidamente, pocos centenas de miles, millones de años. Y ahí entonces se produce una cantidad enorme de polvo. Esa es mi interpretación.
Es decir, vos decís que los pequeños puntos rojos no son rojos porque porque sean muy jóvenes, sino por este fenómeno. Porque eso, cuando aparecieron estos puntos, fue toda una controversia de cómo se habían formado en una época tan joven.
Sí.
Pero no son tan jóvenes.
Bueno, son observados hasta redshift de 10, o sea, desde el punto de vista de la evolución del universo, son jóvenes, ¿no? Pero lo que ocurre es que una estrella de 30 masas solares o 40 explota como supernova en unos pocos millones de años. O sea, y eso no es nada comparado con la evolución. Estamos hablando de 700 millones, este, digamos, periodos, ¿no? De millones, varios millones de años. Mi interpretación es que el polvo se produce inmediatamente, se produce muy rápido. Y entonces es muy difícil ver estos agujeros negros directamente, a menos que sea por medios de radioondas, para lo cual no hay instrumentos todavía disponibles, o infrarrojo intermedio, como el que hay hecho, la única observación que hay con el James Webb, que encontraron en la emisión anual, el infrarrojo intermedio, que quiere decir que hay un centro activo. Además, hay otras evidencias de que los fuentes que son estos objetos y hay muchos modelos ser un modelo natural de edición de todo.